Okay, so this work is mainly done, so this is a mesh-free work. I've introduced you a bit about mesh-free methods. We have talked mainly about point collocation methods, but you can also think about mesh-free methods as Galerkin methods. I think one of the very well explained topics on that area is by Atlouri, who unfortunately passed away. But we have basically the MLPG method, so moving list Petrov-Galerkin. So MLPG is a really, really nice way to think about all mesh-free methods. And if you like, I can also give you a categorization of all these methods, because they can all be formulated within one overarching framework. So the material point method, this is work done mainly by Nguyen Vinh Phu, who is in Monash University. We wrote together this book on the material point method with Alban de Beaucorbeil, so a colleague of Phu. And I just want to motivate a bit what these methods are able to do, because what's really quite interesting is that they are quite related to what we use for the meniscus problem that I showed you earlier today. So Alban is the guy that I was telling you about, who worked with Phu. He's in Deakin University. Sina in Melbourne, and Tushar Mandal, who was a PhD candidate with Phu. And this was funded by the Australian government and Australian Research Council for Phu. Okay, so what you see here is deformation, fracture of solids. So this is a totally different type of problem than what we've talked about until now, in the sense that you have very large deformations and fragmentation. So it's not really a problem with large deformation is usually quite tractable, but some certain problems are, sorry. Okay, certain problems with fragmentation are much more tedious to address than problems related to large deformations, because fragmentation means that you have several subcomponents of the solid, and this is something which can cause quite a lot of issues. Okay, so for example, if you imagine this cube that enters this other cube, this is, for example, a bullet entering a domain or a piece of armor, then you can see that this region is extremely stiff and that one here is much more soft. And the question is, what would be the number of fragments that you end up with? What would be the energy absorbed? Or what would be the velocity of the outgoing component? So that piece that is being thrown out. And that's important for obvious reasons in terms of engineering. And so if you were to solve that using finite elements, the problem would be really quite intractable. And I'm saying this because the idea of mesh-free methods dates back to Monaghan. Of mesh-free methods is clearly dates back to Monaghan, 1975-76, and originally that was really the SPH method. So if you look historically, you start from the smooth particle hydrodynamics, which was written in a quite simple way at the time. Then mathematicians and engineers figured out that there was some instability to this method, tensile instability, and they tried to address it. And many versions of SPH were produced. Okay, so I think that's essentially the main point. And after that, there were some different types of meshfree methods that came about. And then I could give you an overview at some point about the history. It's also given very clearly in our Partition of Unity book that will come out in October with Sundar. But if you are interested, I can give you a very quick overview. Essentially what happens is that in 1994, just at the same time as the Partition of Unity comes about with Melenc and Babushka, who unfortunately also passed away recently. With Melenc and Babushka, we get this idea of Partition of Unity, which I will define in detail in a forthcoming course. But the thing is, with the new meshfree methods of the time, is that they try to address problems related to smoothness of the solution. Right? So the idea is to try to come up with solutions which are smoother, that are, for example, C1 for shell elements, for example, or that have high local reproducibility conditions so that you can reproduce very smooth functions. Or you can also think of cases where you have local enrichment, right? And there are then different topics. There is a notion of intrinsic enrichment and extrinsic enrichment, which I will define in detail in some forthcoming lecture. But suffice it to say now that there were original ideas for meshfree methods were to handle problems such as the one you just saw here, which is fragmentation, delamination, or explosions, where you start with one piece and you end up with a large number of pieces at the end of the simulation. So you have one domain splitting into subdomains. Then the notions of meshfree methods such as elementary Galerkin with Belichko 1994, who also passed away in 2011, as well as the work by Oden, who also passed away this year. This is really a sad year, where he worked on HP clouds and similar methods with Duarte and generalized finite elements. All these methods are based on trying to enrich the approximation. So the idea of meshfree methods in that context is no longer to try to deal with fragmentation and things that split up into pieces, but it's really to have a solution which is high order continuous, enabling things like shell problems, shell elements, or maybe fracture problems if you want to have higher flexibility in the way that you write the approximation scheme. So that you can reproduce any function. I will come back to that. So basically that's the idea of what you want to do with MPM. So MPM is some version of SPH which is much more flexible because it both relies on a mesh and on a set of particles. So typical applications. So you see that thing here is like a tube which is undergoing an explosion. Right? So if you have a tube that is under pressure, for example, with gas or some sort of explosive, and you look at the fracture mode, this is clearly an elastoplastic fracture mode, and you have clear plastic deformations in this tube. And the question is, how do you manage to simulate this? Right? So this is the problem. Similarly, you may want to solve a problem of flow around a sphere in a domain, and that would be something that you could do using particle methods. And these methods are also the ones that we use with DCPSC, with Anas Obeidat, in the work that we are doing on the meniscus. So, okay, I hope that this gives you an idea what the basic ideas are behind the application areas. Okay, so what do we typically do? Well, we typically write the balance equations, so constitutive models, or kinetics, and so on. And we have some geometry, so in that case, this little tube that probably connects to valves. Then we get some equations for that. Very simply, we code in a computer, like finite differences or whatever we solve, and then we get a result, right? So in that case, fragmentation of a piece of something with a bullet or something similar. Okay, so now what are mesh-based and mesh-free methods? Of course, here we're talking, very briefly. Mesh-based, we have a mesh, obviously, by definition. However, it's not so easy in the literature, and that's why we wrote this paper in 2008 with Fu to try to make things clear, because the literature, when I was doing my postdoc on mesh-free methods, was very unclear, and that's how I really figured out how things worked and what was really important. By writing this paper, it was extremely helpful. Also something for young academics. If you ever find a topic which you don't understand, the best thing to do is to write a paper about it, because once you've written the paper about it, you will be for sure really knowledgeable about it. But if you do it properly and you try to make everything crystal clear to the user and the reader, as we did in this 2008 paper, which is now cited, I think, over 1,000 times, I think you will see that this is highly helpful. And also you can think of giving the codes away, because that helps people build confidence and also learn faster. So, okay, what is a mesh, basically? That's the question. So a mesh does many things, and that's why when people talk about mesh-free methods, it is so ill-defined, because a mesh has many, many roles. The first role is to build the approximation. You see here, you have these little nodes, J, and a point, psi G. And what happens with that? Well, I mean, the nodes that you have here are used to build an approximation scheme. So they are used to build what are called shape functions. They are called shape functions because we are usually in an isoparametric element formulation, and in that case, they represent essentially the geometry as well of the element. So, we have polynomial elements, polynomial functions, and so on. So we can just simply do that and compute, and we have now a shape function everywhere which is used to interpolate inside the element. Second role. So what is the second role of a mesh? Why do we need a mesh? Well, usually we use a mesh because we need integration points, like psi G here, right? So what are those things? There are points that you use to integrate the weak form, because you have a weak form. Contrary to what I just presented about point collocation, you have now a weak form, and the weak form needs to be integrated somewhere or other. And we use the Gauss points to do that. Then finally, it's used for post-processing, because we use the Gauss points to post-process. And it's used to represent the geometry of the domain, because without the mesh, we clearly would not be able to represent the geometry. So that's basically what it does. Of course, you have many mesh-based methods, such as finite volume methods, FEM, and even in a way, finite difference methods can be seen as a mesh, except that there is no connectivity per se. The connectivity is not fixed like in finite elements, it's variable connectivity. So not only is it efficient and accurate, but it also has sound mathematical basis. But it has some problems which are related to mesh distortion. So if you really take this element that you see here and squish it completely to make it a line, with all four nodes aligned, the transformation between this element and the parent element will become ill-posed. So you will get a negative Jacobian, which will create huge problems, because you will get negative terms in the stiffness matrix, and this is not something you like on the diagonal, of course, because you want a positive definite stiffness matrix. So that would not be nice, and there are many ways to go around that. For example, strain smoothing stabilization. This is something that, if you are interested, I can talk about. Or mesh-free methods, which are less sensitive to distortion of the mesh. I say less sensitive because my own experience of moving least squares, elementary Galerkin, for example, is that it is quite sensitive, actually, to point placement. And this is also what we see in finite difference methods, where if we have suboptimal point placement, things go quite bad, I have to say. Okay, meaning that we can get results that are completely wrong, right? I mean, at least not convergent. So in meshfree methods, you have points or particles. Example, EFG, as I said, SPH, which is the first one, PFEM, MPM, material point method, and so on. And in that case, the goal is that you are not subject to mesh distortion. Again, this is not so true for EFG, for example, or any method based on moving least squares. My experience is that it is quite sensitive to distortion. And the other problem is that the geometry is not necessarily very accurate because we have only points and we don't know what happens between the points. So we cannot get very detailed cases. Okay, so now what is the material point method? So first of all, you have to know about Solsky because she is the one who came up with the idea. So you can, of course, take a look at what she wrote, and you can also take a look at our latest book. I'll give you a reference. And if you can get it, I think it will be useful reading. Okay, so you have grid nodes, which are here, right? And you have particles. So these particles are superimposed onto the grid nodes, right? So this is something like a mixture between finite elements and particle methods or meshfree methods. Okay, why? Because you have the structure of a mesh, which you will see is used to exchange information between particles. And you have the flexibility of having these particles present in the domain. So you have both, and that is something which is highly desirable. Okay, so now what is included in the particles? You have the position, the volume, the momenta, the stress, the temperature. So all the field variables basically are stored. This is what you are interested in. So there are, of course, many variants of the material point methods, as you can imagine. And the idea is the following. You start with a set of nodes, which are regularly distributed, and you have a set of particles, which are randomly or irregularly distributed, and you exchange information through the nodes. So the nodes that are here, fixed, will have some way of learning from the particles what the values should be. Of course, by interpolation or extrapolation. So that's point to grid. All right, so now if we have some sort of distortion of the mesh, then we can recompute the values at the grid and we can update the grid. And then what happens is that the particles move around and we need now to go from the grid to the particles, right? Because you see very clearly here that now we have a new grid, right? Which moved around thanks to the knowledge of the variables known at the points level. So we have the points, particles to grid. Now we have the data here, we can move the grid. Okay, now that we have the grid, we can project back to the particles, grid to particles, and the particles can then move forward and we reset the grid back to its original position and we keep going. So the grid is basically there to help pass information in a more stable way from particles to particles. So it's like an approximation scheme. And so MPM is really a very cool method because you can deal with really super complex cases. For example, here, large deformations, you see these little beads here, they are actually simulated, right? And you can look at how they deform. It is a really super method. You can look at the Taylor bar example as well, and at these problems of penetration. Similarly, you see here the type of very, very difficult problems that that you can address, of really crushing of a foam. This is absolutely, this is a very, very difficult problem with self-contact. There is a self-contact here at the interfaces. These problems are really difficult to solve. This is not something that you do with finite elements in any simple way. But you see here that the problem is solved fast, let's say, and accurately. And this is done by image-based analysis with huge deformations, really enormous, with self-contact. Then explosions, and fragmentation is something that you can do. So this is very nice. This is called hypervelocity impact with Johnson-Cook model. Really huge simulations with Caramello. There is no mesh generation, very simple basis functions, very large deformations, automatic no-slip contact, also multiple contacts can be done, and simple boundary condition treatment, simple implementation. So, but there are some issues which I don't know if we'll have time to talk about today, but at least I will talk about the issues, but not about how to resolve them, because we have 11 minutes left, I think. So it would be better to have some questions and discussion. So what are the issues? And they are very similar to what I was talking about in SPH at the beginning. So if you look at these two annula that are colliding, so what is that? Clearly, that's not something that you want, because this is not a structural effect at all. So we'd like to get rid of this. And this is called cell crossing instability. So let's look at what that means. So in total Lagrangian, you have the balls that fall, and everything comes back to the original configuration. And in the standard way, you see that you don't have that. You have direct separation between the two, right? And so this is what you actually do not want, right? So you have here this virtual crack, which should not happen. So this is known as numerical fracture, and this is very, very well known in SPH because it was known as tensile instabilities. And well, I think I will not go into these details now, because otherwise it would probably take another half hour, and we don't have this half hour now. I think I would rather go back to you and ask if you have maybe questions, which would be really nice. And then, yeah, I'm looking forward to hearing ideas about what we could talk about